In this video, we're going to look at the dimension of the column space of a matrix. We're going to see a famous result in linear algebra that the dimension of the column space of a matrix is equal to the dimension of the row space of the matrix. Recall that we defined the rank of a matrix to be the dimension of its row space. We saw that the dimension of the row space of a matrix was equal to the number of non-zero rows of the matrix in row echelon form. What we're going to see now is that the dimension of the row space is equal to the dimension of the column space. This result is also referred to as row rank equals column rank. This is because the row rank is defined to be the dimension of the row space, and the column rank is defined to be the dimension of the column space. So we're going to show that the dimension of the row space is equal to the dimension of the column space, or in other words, the row rank is equal to the column rank. We're going to show that the row rank is equal to the column rank in two steps. First, we're going to show this result in a special case. We're going to show that if a matrix is already in reduced row echelon form, then its row rank is equal to its column rank. Then in the second step, we're going to show that the dimension of the column space of a matrix is equal to the dimension of the column space of its reduced row echelon form. If we do both of these things, then we will have finished the proof. The reason is the following. The row rank of a matrix A is equal to the row rank of the reduced row echelon form of A. Remember, this is true because we saw that doing elementary row operations didn't change the row space of a matrix. So the row space of A is the same as the row space of its reduced row echelon form, and therefore the dimension of these two spaces is the same as well. Now part 1 is going to tell us that the row rank of the reduced row echelon form is equal to the column rank of the reduced row echelon form of A. And part 2 is going to tell us that that is equal to the column rank of A. And now, through this chain of equalities, we will have that the row rank of A is equal to the column rank of A, which is what we wanted to show. Now, there's an important thing to take note of here. That's in step 2. We're only showing that the dimension of the column space is equal to the dimension of the column space of the reduced row echelon form of A. Actually, in general, it's not going to be true that these column spaces are the same. The column space of A can be different from the column space of the reduced row echelon form of A. But what we will show is that although these spaces can be different, they do have the same dimension. So that's an important thing to keep in mind as we go ahead. Alright, let's go ahead and start with the first step. So now we have a matrix in reduced row echelon form, and we want to show that for such a matrix, the row rank is equal to the column rank. So here we have a little example of a matrix in reduced row echelon form. And what we're going to claim is the following, that the columns with leading entries form a basis for the column space of this matrix. So again, leading entries are the first non-zero entries in a row. So this matrix has 2 leading entries, and that means that the first column and the third column are the columns here with leading entries. We're going to refer to these as pivot columns because they're columns that contain the pivots. So the claim is saying that in this case, columns 1 and columns 3 will be a basis for the column space of this matrix. Okay, and now notice that if we show this claim, then we will have actually shown and finished step 1, right? Because the number of leading entries is simply the number of non-zero rows in our matrix, right? That's what determines how many leading entries there are, is the number of non-zero rows. And we already know that that's the row rank of this matrix, right? It's just the number of non-zero rows. So if we show that these columns that have leading entries are a basis for the column space, well, the number of such columns will just be the number of pivots, the number of non-zero rows. So that will have shown that in this case, the row rank is equal to the column rank. Okay, so let's go ahead and show this claim that the columns with leading entries form a basis for the column space of a matrix in reduced row echelon form. So we have to show two things to show that these columns are a basis. We have to show that they're linearly independent and that they span the column space. So let's go ahead and start with linear independence. So what we can do is we can form a matrix R tilde whose columns only consist of the pivot columns of R. So in this case, we have pivots here and here. These are the leading entries. So our pivot columns are again columns 1 and columns 3. And now imagine that I form a new matrix, R tilde, where I just delete these columns that aren't pivot columns. Okay, I delete the free columns of the matrix. And now you can see that if I delete all the free columns of R, then I'm left with a matrix, R tilde, that has no free columns, right? Every column of R tilde will have a leading entry. Okay? So therefore, since R tilde has no free columns, if we look at the equation, R tilde times x is equal to the all zero vector, this equation will have a unique solution because R has no free columns. Okay, so the only solution to this equation will be when x is the all zero vector, right? The trivial solution. That in turn means that the columns of R tilde are linearly independent. The only solution to R tilde times x is equal to the all zero vector is the trivial solution, where x is itself the all zero vector. What that is saying is that the only linear combination of the columns of R tilde equal to the all zero vector is the trivial combination, where all the coefficients are 0. Therefore, the columns of R tilde are linearly independent. Now let's see why the pivot columns span the columns of R. So say that R has little r many non-zero rows. So in our example here, R has 2 non-zero rows, so little r would be equal to 2. And notice that every column is of this form. So it can have some arbitrary entries in the first r coordinates, y1 through yr, but after that it has to be 0. So in our example here, the third coordinate of every column vector is 0. So any vector of this form can be spanned by the following r many vectors. So these are vectors where we have a 1 in one position, say the ith position, and zeros everywhere else, as I ranges from 1 to r. So for example, this vector has a 1 only in the first coordinate, and this vector has a 1 only in the rth coordinate, and in between we have the vectors that have a 1 only in the second coordinate, third coordinate, etc., up to r. So any vector of this form we can write as a linear combination of these r many vectors. And now we just have to notice that these r vectors are exactly our pivot columns, right? Because each pivot column has exactly 1, 1. So this pivot column has a 1 only in the first coordinate. This pivot column has a 1 only in the second coordinate. And moreover, these pivot columns have 1s in distinct rows, right? That's the nature of a row echelon form. So therefore, these R many pivot columns are exactly these R vectors. So this shows that the pivot columns span the columns of a matrix in reduced row echelon form. This finishes the proof of step 1. We've shown that in the special case of a matrix in reduced row echelon form, the row rank is equal to the column rank. We did that by showing that the pivot columns form a basis for the column space of a matrix in reduced row echelon form. And the number of pivot columns is equal to the number of pivots, which we've already seen is the row rank. In the next video, we're going to show step 2, which will then finish the proof.